Hello again. Today we're going to be talking about a special technique of integration called integration by parts. So let's get started. I want you to think back to the product rule because we're going to need to alter that a little bit so that we can carry out this technique. The product rule said that if we have two functions, u of x and v of x, then the derivative of the product of those two functions would be the first function times the derivative of the second one plus the second one times the derivative of the first. And I've kind of written it in that notation right there. If I integrate every term in this equation, what I can get is that equation right there, just with integral signs in front of each one. But I notice that on the left-hand side, I have exactly the integral of a derivative. So that's just going to be uv on the left, and then the dx's can cancel out on the right-hand side, and that just gives me the integral of u dv plus the integral of v du. Now, if I rearrange this a little bit by subtracting the integral of v du from both sides, then I get that the integral of u dv equals uv minus the integral of v du. Now, that doesn't really make a whole lot of sense by itself, but that's actually the equation that I need to do every integral that I need to do by parts. Okay, so if I have that equation, that's the same one from before, I'm going to look at every integral that is the integral of a product, and I'm going to see if I can use this method to do it. So what I have to do if I have the integral of a product is I can call one part of it u and one part of it dv so that it looks like the expression on the left, and then I can rewrite it as the expression on the right, uv minus the integral of v du, and hopefully I can evaluate that integral v du more easily than I could when it was originally given in the question. So the problem is I have to figure out which part of that product I have to call u and which part I have to call dv. So what I do is I use an acronym, a little mnemonic device called detail, and here's how it works. I'm going to choose dv first, and then whatever I don't choose as dv, that is going to be my u. So dv is chosen by the following hierarchy. If I see an exponential function, that is going to be my dv, and the other part will be my u. If I don't see an exponential, then I will look for a trigonometric function, and that will be my dv, and the other part will be my u. And if I don't see either of those, I will look for an algebraic function like a polynomial, and if not any of those, I will look for an inverse trig function, and finally I will look for a logarithmic function. So just remember the word detail, and that will tell you what functions to look for first and call those dv. The other function will then become u. All right, so let's look at an example. So I have the integral of x times e to the x. And so remember, I'm looking for which one of those to call u and which one of those to call dv. Well, I see an exponential there, it's e to the x, so that will be my dv, meaning that the other part, which is x, is going to be my u. All right, so now what I can do is I have the left-hand side of that equation figured out, so I can write the right side. But to do that, there's some things I need to figure out first. I need to figure out what v is, and I need to figure out what du is, because both of those appear on the right-hand side of that equation. Well, v is simply going to be the antiderivative of dv, so that's also going to be e to the x. Du is going to be the derivative of u, which is just 1 dx, or I can just write it as dx. So now I have everything I need to write the right-hand side of that equation. And so uv minus the integral of v du becomes x times e to the x minus the integral of e to the x dx. So now all that's left to do is to figure out what the integral of e to the x dx is. And I do know what that is. That's actually e to the x plus c. So I can finish the question and say that the answer is x times e to the x minus e to the x plus c. And that finishes that question. So let's look at another example. Let's say I have the integral of 4x times the natural log of x dx. Now I didn't see any exponentials or trigonometric functions here, so I went down to an algebraic function, which is 4x. That's going to be my dv, meaning that the other part, natural log of x, that's going to be my u. And so now I have the left-hand side figured out. I have my u dv. But to write the right-hand side, I need to figure out what v is, and I need to figure out what du is. And again, v is the antiderivative of whatever I chose dv to be. So that's going to be 2x squared. And du is going to be the derivative of whatever I chose u to be. And so the derivative of natural log of x is going to be 1 over x dx. Now I'm ready to write the right-hand side, which is uv minus the integral of v du, and I just plug things in. U is natural log of x, v is 2x squared, minus the integral of v du, which is 2x squared times 1 over x. And I can actually simplify 2x squared times 1 over x. That's actually just 2x dx. And so now all I have to do is figure out the antiderivative of 2x. That's x squared plus a constant. So my final answer is 2x squared times the natural log of x minus x squared plus c, and that question is done. Now sometimes it takes more than one iteration to do this. So let's say I had x squared times the cosine of x. Remember, I'm still looking for dv first. I did find a trigonometric function that was cosine of x. So that's my dv, meaning that x squared is my u. Now I just need to figure out what v is, and I need to figure out what du is, the same way that I did them before. And I write my uv minus the integral of v du as x squared sine x minus the integral of sine x times 2x. Now the problem here is I don't know the antiderivative of 2x times the sine of x. So I really can't proceed any further. So what I have to do is I have to look at that integral, and I have to do integration by parts again. So sine x is another trigonometric function. That will be my dv this time, and 2x will be my u. And again, I figure out what v is, and I figure out what du is, and I proceed from there to get x squared sine x. That was from the first time that I did integration by parts, and now I have to do the uv minus integral of v du again, and that gets me 2x times negative cosine of x minus the integral of negative cosine x times 2 dx. All right, and I do know what the integral of that is. That's negative 2 sine x plus c. So that question took a couple of times to do integration by parts, but I still got to the right answer. So if it's going to take more than that, I should probably come up with a shortcut for that, and luckily there is one. And you can use this shortcut whether you're using integration by parts once or multiple times. So what I do is I make a table with two columns. One of them is u and one of them is dv, based on what I choose from the very, very beginning. So let's use this method for a question like the integral of x to the fourth times sine of x. Sine of x is a trigonometric function, so that's going to be my dv, and my u, therefore, is going to be x to the fourth. So here's how I proceed. Along the left-hand side, I'm going to write plus and minus, alternating down throughout the rows of the table for as many rows as I need. So I'm going to take the derivative of whatever u is over and over again in that column marked u, and I'm going to take the antiderivative of whatever's in the dv column over and over again. But each time I do that, I look across the row and I multiply those two functions together, and I see if I do know the antiderivative of that. And if I don't, I keep going. Well, in that last row, I've written 4x to the third times negative cosine x, and I don't know what the antiderivative of that product is. So I keep going, and 4x to the third becomes 12x squared. Negative cosine x becomes negative sine x. I keep taking the derivative in the u column and the antiderivative in the dv column. So that's still not something I know. I don't know the antiderivative of 12x squared times negative sine x, so I keep going. 12x squared becomes 24x, and negative sine x becomes cosine x. Still don't know what that is, so I keep going. 24x becomes 24, and cosine x becomes sine x. I do know the antiderivative of 24 sine x, so I can stop here, and now I just need to write my answer. Well, here's how I do that. I read the signs and diagonals until the bottom row, which is still inside of an integral. So I'll kind of show you what I'm looking at and what I'm going to write down. So I look at the positive, the x to the fourth, and the negative cosine x, and I multiply all that together, and that gets me negative x to the fourth cosine x. So that's the first term in my answer. And then I keep looking at the diagonals. I've got negative times 4x to the third times negative sine x. That is positive 4x to the third sine x. I keep going. I've got positive 12x squared times cosine x. I've got negative 24x times sine x. And now I'm at the bottom row. I've run out of diagonals, so I look at the bottom row and I read it across, but I still read it as an integral. So I'm going to add the integral of 24 sine x. And this is why it's important for you to know that antiderivative, because you actually have to write down what the antiderivative of that is. So the antiderivative of that is negative 24 times the cosine of x. Everything else stays the same, but I write that as negative 24 cosine x plus my constant. And I would have had to do integration by parts like 4 or 5 times to get there, but this saves me a lot of time by making this table. There's a special case I need to consider if there's a cycle. So I'm going to try e to the x times the cosine of x and watch what happens. If I use detail, then dv is e to the x and u is cosine of x. And so watch what happens. I'm going to keep taking the derivative of whatever's in the u column, and I'm going to keep taking the antiderivative of whatever is in the dv column. So my next row has a negative sine x under the cosine x, and it has an e to the x under the e to the x. I still don't know what that product is. I don't know what the antiderivative of that product is, so I keep going and I get negative cosine x and e to the x again. Well, this is going to create an endless cycle of sines and cosines in the left column and e to the x's in the right column. So it looks like I'm stuck, but let's see what I have. If I write down what I have so far, I have that this is equal to positive cosine x times e to the x, and then positive e to the x times sine x, because those two negatives cancel out. And then looking at the bottom row, that still has to be in an integral, so it's the integral of e to the x times cosine of x. So that's what I have so far. But if I look at what I have so far, the integral on the left-hand side and the integral on the right-hand side are exactly the same. So what I can do is I can combine both of those on the left-hand side of the equation by simply adding the integral of e to the x cosine x dx to both sides. So now I have 2 of them on the left and none of them on the right. I just have an expression with no integrals on the right-hand side. So I have 2 times my question equals e to the x cosine x plus e to the x sine x. So all I really need to do to figure out my answer is divide both sides by 2, and I get that the integral of e to the x cosine x dx is going to be e to the x cosine x plus e to the x sine x all over 2 plus a constant. And that's how you do integration by parts. We'll have a lot of opportunity to practice this, but for now, if you have any questions, please let me know, and I will see you tomorrow.